Poker heads. So cards, they're a classic playground for combinatorics. Just so many fun counting problems come up very naturally in that setting. Um, and coffee, a very necessary prerequisite for combinatorics in all settings, such as cards. So classic question. How many ways can you deal four of a kind in poker? So I'm thinking standard, 5-card poker, right? 52 card deck. And here's an example of what four of a kind would look like. What do we mean when we say four of a kind? Say you were dealt all 4 queens and then a 7, right? That would count as four of a kind. You really don't care what that 5th card is. The important thing is that you have all 4 of one value, right? So how can we count how many ways there are to do this? Well, it would be kind of a lot to enumerate all of these, right? So here's a nice way to think about it. First, let's think about what values or denominations, appear, right? So in this setting, what do I have? I have queens and 7s. That's what I have in my hand, right? So let's just ask what values appear in my hand. That's the first thing that will count on our way towards figuring out how many four of a kinds there are. So there are a lot of ways. There are going to be exactly 2 of them, right? So maybe if I have 4 of a kind, right? In 4 of a kind, I have exactly 2 values. So maybe I have aces and 2s. Maybe I have aces and 3s. Maybe I have aces and 4s, all the way up to aces and kings, right? And then maybe I have 2s and 3s, 2s and 4s, and so on, all the way up to 2s and kings, right? And so on, so on, so on, right? You could imagine listing out all the ways we can have just two values appearing in our hand, right? So what would this be? This would be, what would the length of this list be if I was saying this list here? How many items are on this list? Well, this would be 13, choose 2, right? That's the number of ways to select 2 values out of 13 possible, right? Ace through king is 13 options. And I want to choose exactly 2 of those to appear in my hand. Next, after I do this, so this is the first thing you need to decide is what values appear, right? Next, I'm going to decide which do we have 4 of, right? One of those values you're only going to have 1 of, and one of those values you're going to have 4 of. So say from aces and 2s, you could either have 4 aces and a 2, which if you read it sounds like a sneeze, right? There we go. The coffee kicked in apparently. Or you could have 4 2s and an ace, right? You could have 4 aces and a 3, or you can have 4 3s and an ace, and so on, right? So pretty clearly there are 2 options for each of these selections of values. There are 2 options for each of those. So this looks just like the tree diagrams we drew during fundamental principles of counting, right? So you'd multiply by 2 for so this is the number, the 13 choose 2 is a number of ways to pick 2 values, right? Out of 13. And then this is the number of ways to decide which value you have 4 of versus which value you have just 1 of. Right, which value appears 4 times. That's the 2, right? So that's this next branch in our tree diagram. Now, the next thing we need to do is we need to pick the suits. Now, for the card that we have 4 of, there are no options there, right? If you have all 4 aces, you have all 4 aces. You have all the suits. You have exactly one ace of hearts, aces of diamonds, ace of spades, and ace of clubs. You have all of them, right? There's only one way to do that. But we have some flexibility on the say on the two, on the two hand, we have some flexibility on the suit of the two, right? What is the suit of the single card? Right, that's where we have one more decision to make. So here, right, if I fill in the suits, right, the aces, I know I have all four aces. I have ace of hearts, ace of diamonds, ace of clubs, ace of spades. But then the two could be hearts. The two could be diamonds. The two could be clubs. Or the two could be spades. Right. So there we go. I have 1, 2, 3, 4 choices of how to fill in the suits. And from this one, I'll have 4 choices, depending on hearts, clubs, or spades for that ace, and so on all the way down the line, right? So I'll have my tree diagram will, again, grow by a multiplicative factor, right? Everything is growing uniformly here. So this will go up by a factor of 4. That's the number of ways to pick the suit, right? To pick the suit of the single card. Right, that's our 4. So if we multiply all of this together, we'll get the number of ways to deal 4 of a kind in poker, right? So this would be what I would have. The total then is 13 times 12 over 2 times 4. The 2's cancel, so I get 13 times 12 times 4. So 13 times 48, right? So what's that? 480 plus 3 times 48 is 120 and 24. There we go. Right. So 504 and 120. There we go. Right. So I get 624. So there we have the number of ways to deal 4 of a kind in poker. And this I think is actually a very nice, very natural place to then mention probability, right? Just briefly, I'm not going to dedicate the whole video to it, but this is actually the really hard part, getting this 624. If you wanted to say, what's the probability of being dealt 4 of a kind, right? So if you want to say, what is the probability of being dealt 4 of a kind in a 5-card hand, right, in standard 5-card poker, well, what's it going to be? We just counted how many ways you can be dealt 4 of a kind. So all we need to do is take 624 out of the total number of hands of 5-card hands, right? Which, what do you do when you deal a 5-card hand? You choose 5 cards out of 52, right? You're choosing 5 cards out of 52 to be dealt. And this gives us our probability as a fraction, right? Which, to just grind this out, if you have, so 52, choose 5, just to see that as a number, is going to be 2,598,960, right? So there it is as a fraction, which you can see as, just as a fraction, right? It's pretty difficult to be dealt 4 of a kind, because that's roughly 600 out of 2.5 million, right? That's that's why it's a strong hand, right? It's hard to be dealt that. And if we get this as a decimal, right, we're going to have, if we just to get a decimal approximation, just to, usually with probability, you express it as a percent, right? Is a very standard thing to do in probability land. What does this become? It's 0.00025, sorry, 4, right? Is the is if you express that as a decimal, roughly, which becomes 0.024%, right? So significantly less than 0.1% chance of being dealt 4 of a kind. That's pretty rare, right? But the point of this is a lot of very frequently in probability questions, the really tough part is some counting argument, right? And we'll visit the idea of probability more thoroughly later. But this is a classic counting problem, and from that counting problem, it's not too much more work to answer a very related problem in probability. So, all right, let's look at a slightly trickier poker hand. Let's look at a follow-up question. It sort of turns out in poker, for the most part, the easier the hand is to get dealt, the harder it is to count, right? Because the really rare hands are easier to count because they don't appear very much. So that's right. The easier the hands that are easier to be dealt are harder to count because there's so many of them. So let's say, how about what is the probability? What's the probability of being dealt, let's say, 2 pair? Let's see that, right? In poker, right? So what's the probability that we're dealt 2 pairs? So this would be something like, say you were dealt a pair of queens and a pair of jacks and a 7, right? Say that was that. So that would be called 2 pair, right? So the fifth card, it needs to be different from either of the first 2 values, right? It can't be the same as a queen and the same as jacks, because then it's not called 2 pair anymore. Now it's called the full house. And so here we'll take an approach very similar to what we did up here. Let's start by asking what values appear in our hand, right? Which values do I see? Right, which values appear? So, well, here, what do I need? I need 3 out of the 13 possible values have to appear in my hand. And once again, you think of this as a tree diagram, right? Okay, I can pick, I could have aces, 2s, and 3s. I could have aces, 2s, and 4s. I could have aces, 2s, and 5s, and so on, right? I could have, then, just, I'm going way out of sequence here, but just to say, at random, I could have, 7s, 10s, and queens. I could have 7s, jacks, and queens, right? That's one that I'm sort of demoing above in my example there, right? You can have all the way up to, jacks, queens, and kings by the sort of pseudo alphabetical thing that I'm doing here. So first we're saying, which values do we have in our hand? Well, there are 13 choose 3 ways to pick those. From those, though, I have a lot of decisions to make. I need to decide which value do I have just one of versus which values do I have pairs of, right? So let's call it the loner, right? Which value is the loner, right? Which up here, 7 would be the loner, right? So here, like I could pick, for example, here, 3 could be the loner, right? 2 could be the loner, or ace could be the loner, right? And I could do this for any of these, right? So again, here, 4 could be the loner, 2 could be the loner, or ace could be the loner, and so on, right? And just to see our example hand up above, right, that would be on this part of the tree. So here I could say that queen could be the loner, right? I could say that jack could be the loner, or I could say that 7 could be the loner. right? So there's the our example hand appearing in this tree. So that gives me 3 options per choice of values, right? I have 3 options now for who is the loner. All right, great. Next, what do we need to do? Suits, right? There's a lot that we need to do here, because we need to pick suits for all our cards, right? So we need to pick suits for the pair. For one pair, we need to pick suits for other pair, right? And we also need to pick suits for the loner, right? This is what we need to do. So how can I do this? Well, let's look at just one of these, and I'm going to actually look at our example hand here, right? Because I want one in the middle, so I have lots of space. So this same argument is going to work, coming off of any of these, but I'm going to look just at the Jack, Jack, Queen, Queen, 7 hand. So I want to pick the suits for pair 1. So what am I doing? I'm saying, okay, what could the jacks be wearing? I could have hearts and diamonds, right? I could have hearts and clubs. I could have hearts and spades, right? I could have diamonds and clubs. I could have diamonds and spades, right? Or finally, I could have spades and clubs. So this is, there we go. I've found all the ways of picking the 2 suits that will go on the jacks in my hand, right? Out of 4 possible suits. Okay. So what is that? That's 4 choose 2. That's what this list is right here, right? I listed out all the ways of selecting 2 suits out of 4 possible for my jacks to wear, right? Well, this, fortunately, 1, 2, 3, 4, 5, 6. This again is going to grow by a factor of exactly 6 when I pick the suits for the queens, right? So now I'm going to have things like Jack, Jack, Queen, Queen, 7, and this will be hearts, diamonds, say, right? And then the next one, Jack, Jack, Queen, Queen, 7, hearts, diamonds, hearts, clubs, and so on, right? So I'm going to have 6 options for each of those. And then lastly, we'll pick the suits for the loner. Well, there are 4 ways to do. And you can think of that 4 as 4 choose 1 if you want, or you could just think of it as 4. There are 4 options to pick the suits for the loner. Right. So from each of these, you'd have 4 growing off of this. So you'd have Jack, Jack, Queen, Queen, 7. Here the jacks and queens are in hearts and diamonds, and the 7's in a heart. But then you're gonna have 3 more just like it, right? With a different suit on the 7. So a heart, then you have the 7 of diamonds with those hearts and diamonds, and so on, right? And there will be 4 branches for each of those previous on this tree, right? So then multiply them all together, right? Multiply them all together, and we'll get our result, right? So this will be the number of ways to deal 2 pair, right? Will be the product of all these quantities. So it's going to be 13 choose 3, right, times 3 times 4 choose 2 times 4 choose 2 times 4, right? That product, that will give us the number of ways to get 2 pair, right? So this will be 13 times 12 times 11 over 3 times 2 times 1, right? Times 3 times 6 times 6 times 4. And we can, of course, do some cancellation, right? You can cancel the 3's. You can put a 2 into a 6 and make it a 3 instead, right? And that's about as much as it cleans up, right? So we have, at the end of the day, we have 13 times 12 times 11 times 3 times 6 times 4, right? And if you grind all of that out, we should get the number of 2 pair, right? So 13 times 12 times 11 times 3 times 6 times 4, right? At the end of the day, we get 123,552, right, ways to deal 2 pair. There it is, right? So that's our total count on those hands. And if you wanted the probability, right? Well, fortunately, we already have the total number of hands. This is a fairly common hand in poker terms, at least. We already know the total number of hands is this 2598960, right? So 2598960, 1, 2, 3, 5, 5, 2, right? This will give us the probability of being dealt 2 pair in poker, right? So it'll be this number divided by 2598960 produces 0.0475 roughly. And so as a percent, right, this is actually a pretty substantial percent, right? This is about 4.5%. Sorry, 4.75%, right? Way more likely than 4 of a kind, right? 4 of a kind, we were talking, what was it, 0.02%? Yeah, 0.02% versus 4.75%, right? Far, far, far more common to get 2 pair in poker. Which, of course, is why 4 of a kind beats 2 pair, because it's a more rare hand. You were luckier if you got 4 of a kind. So, all right, great. Thanks so much. Classic counting applications.